Hi everyone, I'm Robin Carpentier and I am one of the co-authors of the demonstration paper titled An Extensive and Secure Personal Data Management System using SGX. First, let me introduce some context. Personal data management systems, or PDMSs, are flourishing, boosted by legal and technical means like smart disclosure, data portability, and data at rhythm. A PDMS allows its owner to store and manage data directly generated by their devices or resulting from their interactions with companies or administrations. This paradigm unlocks innovative usages by crossing multiple data sources from one or many users, but it requires the PDMS to be easily extensible. Yet, its security is also of paramount importance since it potentially stores the entire digital life of its owner. This demonstration describes the first implementation of an extensive and secure PDMS on an Intel SGX platform. Intel SGX is a hardware security mechanism providing a secure execution environment named Enclave, having three properties: isolation and attestation of the enclaved code, and confidentiality of the enclave's data. Moreover, recent works propose to add sandboxing techniques to enclaves to prevent malicious code from disclosing confidential data. Our extensive and secure PDMS architecture is based on SGX and sandboxing properties. As an example of scenario, let's consider companies offering their employees a green bonus, which is an ecological incentive based on the number of commutes by bike. The computation is done by the employee's PDMS, which collects GPS traces from a reliable service like Google Maps, then computes the number of bike trips between home and work, and finally provides the result to the employer. This scenario involves three requirements. First, data privacy must be protected such that the employer cannot access the detailed GPS history of the user. Second, the result must be verifiable by the employer. It must have been computed by the correct code on genuine data. Finally, the collection and computation codes are rather specific, thus the need for extensibility. To answer these requirements, we propose the three-layer architecture with a secure core, isolated data tasks, and untrusted applications. The core is a minimal trusted code base. It implements basic operations on personal data and runs inside an SGX enclave. Data tasks extend the core and can only communicate with it. They are entrusted by the PDMS owner and run inside SGX enclave and are sandboxed. Any communication is secured using TLS. The core acts as a proxy for the tasks, keeping the credentials of the connection secret. For instance, the core opens the connection with Google Maps in lieu of the collect task. The input-output of tasks are regulated by the core, which enforces access control rules. Attestations and signatures are provided in a manifest file and verified during the computation, resulting in an end-to-end attestation. With these five properties, we ensure extensibility, verifiability, and privacy. More advanced properties are described in the paper. We developed a PDMS prototype on real Intel SGX hardware in C++ using the Open Enclave SDK. This prototype contains a web interface developed with Witty, allowing to interact with the elements of the architecture previously described. First, we set up the platform and an enclave containing the code of the core. The core is loaded with credentials needed later for the data collection. We also launch a local HTTP server, which acts as the data provider. This HTTP server contains the GPS locations of the user as a JSON file. On the left of the execution page, execution traces of the core will be displayed and components will be highlighted when used. The same design on the right covers the execution of the data collectors and computation tasks. The execution can now begin. Initially, the core is running and waits for computation. By selecting the Collect GPS scenario, an enclave containing the code of the data collector is launched and registers with the core. The core verifies that the enclave code measurement matches the one in the manifest file and opens a TLS connection with the collector. Then, the collector asks the core to collect to the HTTP server. The core retrieves from its own database the user credentials that are needed to authenticate on the HTTP server. After the authentication, the collector can issue one or several HTTP requests to the server, the core acting as a bridge. The collector sends a request for the locations of the user. In our scenario, the server answers with the JSON file previously shown. The collector receives the locations, extracts tuples from the file, and sends them to the core. The core checks the database access rights of the collector and then inserts the tuples in the user database. Now that the data are collected, the computation of the number of bike trips can begin. An application representing the employer sends a computation request to the core. Another enclave is instantiated containing the computation code. It registers with the core in the same way as the collector did. The core retrieves the GPS data from the database and sends them to the task alongside the home and work locations. The task computes the number of bike trips between home and work and returns the result to the core. The result is then transmitted to the application. The second part of the demonstration is devoted to 3 interactive games that can be experienced through the demonstration website. These games are made to ease the comprehension of our security properties and their impact on attack mitigation. They simulate either a malicious employee who wants to obtain a larger green bonus or a malicious employer spying their employees. Some security properties of the PDMS are enabled or disabled, and the player must guess the impact on the result of the computation. Thank you for your attention.